Okay, let me give you an overview of where we're headed for today, just so you know the sorts of problems that we're working on. You've taken algebra courses maybe recently in your math education. If not, this is a standard problem in any algebra course, and the goal is to find the solution to a system of equations, and these are linear equations where you have x to the first power and y to the first power. They come in all different kinds of shapes and sizes, and we have all kinds of techniques that we can use to solve these. And for example, this one problem here is where we ended last time, and so that's where we'll begin. And there was this matrix here, and we started looking at row operations. These row operations that we're going to be doing will be used later on in linear programming. So it's important to get a sense of how to do these row operations by hand now. I'm not going to do row operations using the calculator function. I think the row operations on the calculator are harder to learn than the row operations themselves. So anyways, this is a problem, and if you put x's and y's, and I'm just going to call this one over here the right-hand side and abbreviate it RHS for right-hand side. The problem that you come up with is exactly this one. This one right here. And there was the matrix. So you can just see, you bring down the coefficients and solve the problem that way. And there are several different techniques. There's the substitution method, where you substitute from one equation into the next, and eventually back substitute and find the value for x and find the value for y one at a time, and then put them together as your final answer down here. And you can check that answer. Another algebraic method for a 2x2 system is the elimination. And I'll include this in the notes, you don't have to write it down. And this is the one where we multiply an equation by a number and then add it with the other equation. Something cancels out. You're able to find the y or the x first, in this case the y, and then you go back and repeat this method over here to find the x. If you convert both of these equations and solve them for y, you can enter y1 into the first equation into y1, and the second one, or at least an equivalent version of it, in y2, and then graph them both, and the point of intersection is the solution. Now, the matrix method that maybe you've never learned is what's going to be the focus of today. Now, you're going to see it. It's going to be tedious for you. We're going to apply a lot of row operations. You're going to wonder why in the world we're using it. But eventually, the calculator can do this Gauss-Jordan method, and all you have to do is enter in the matrix, and it'll spit back another matrix where you can interpret your answer. So I have to show you how to enter the matrices into the calculator, how to run the Gauss-Jordan and put the matrix into what we call reduced row echelon form, and then how to interpret the answer matrix so that you can get an answer that looks like -1, -2. So that's where we're headed today. And the beauty of Gauss-Jordan is that it works instantly. It's always the same for any size system. So you can go 2x2 system, the simplest ones that you learned in elementary algebra, or you can do a 3x3 system. The algebraic methods on those are very, very tedious and long. Use 2 or 3 pieces of paper just to work out the work. And then you can even do 4x4s that are pretty much unheard of in an algebra course just because the algebra is so tedious. But for the calculator, it can do these problems instantly and come up with the solution. Notice that just 2 of you have your cameras on. I like seeing your faces when I talk instead of just a bunch of black boxes with names in them. So if you would you turn on, I know not everybody is comfortable with this, and that's fine, but would more of you turn on your cameras, and so I can see you. And of course, you know, if you need to turn it off, then you can turn it off. If you have a strong Wi-Fi connection, then it shouldn't matter that your face is showing. All right, so let's go here. And let's work on this one. And here's kind of the goal. Here's kind of the goal. If we can use row operations, and I'll just call this work behind the scenes. If we could change that matrix to one that looks like this, same dimensions, 2 rows, 3 columns. If we can change it using correct legal row operations from this form to this form, then we can write down an equation for each row. The first coefficient is the x, the second coefficient is the y, and then on the other side of that vertical bar is the number that appears in the right-hand side. So if we wrote this first equation, it would be 1x plus 0y equals -1. 1x, 0y, -1. If you write the second equation, then that would be 0x plus 1y equals -2. Now there's a simpler way to write the first and the second equations. So if you can get the solution or the matrix in this format, then you have the solution, because the solution is just x coordinate -1, y coordinate 2, and there's the answer. And notice that the answer appears vertically in that last row over there. So here's what we're going to do to solve these systems. They can be 2x2 systems where you have 2 equations and 2 variables. They can be 3x3 systems where you have 3 variables and 3 equations. But ultimately, we're going to look for the solution in the last column if one exists. So the goal is to convert this matrix to this form, and then we have the answer. If we were to do this by hand, it would take a lot of work. It would take a lot of tedious work. So we're going to let the calculator do this. And the name for a matrix in this, where we have ones down the main diagonal, and we have zeros above the diagonal and zeros below the diagonal, this is called reduced row echelon form. So the goal is to start with a matrix and put it in reduced row echelon form. If you create an acronym with the first letter of each one of those words, it looks like this, RREF. So when you see that, you're asking the calculator to take a matrix and put that matrix into reduced row echelon form. And then your job is to interpret that matrix to find the solution. All right, so I'm going to walk through the calculator steps now for that. And so you're going to want to write these down somehow, and I'll write them down as well. The first thing you're going to want to do is to enter the matrix. Now we're talking about, these are calculator steps. So what I'm doing is I'm showing you how to use your calculator to start with this matrix, and we have to enter in that matrix right there. That's the original problem, and how to convert it to this format here so that you can pick out the answer. So I'm going to start with, as my example, this same one. We know what the answer is. The answer is -1, -2. The first thing you need to know is that this is a 2x3 matrix. So the first thing you want to do is to hit the second key and then the x to the -1 key. If you'll notice, the second key is the blue, and so right above the x to the -1 is this menu called matrix. See if I can show it for you there. Here's x to the -1, and right above it is matrix. So when you want to enter a matrix, or when you want to do some row operations, when you want to do RREF to convert a matrix into that special form, then you always want to start by pressing the matrix key. And when you do that, this is what it'll look like. The first menu has just a listing of all the names. It looks like you have 7 matrices there that you can actually input at the same time, and even more because there's an arrow down there. I have a bunch of matrices already entered into my calculator. Yours might look blank at this point. If you go over one menu, this is where we do the math calculations of a matrix. And so if you scroll down, you'll see the math function that we're interested in. It's right here. You see it? RREF, reduced row echelon form. That's what you're after. And where you want to start, however, is in the Edit menu. Because the Edit menu, if you think about the Statistics menu, where you enter in your data, that's the Edit menu. They're consistent here. If you want to edit a matrix, where you want to enter in a matrix, you go to the Edit version. So when I go to Edit, the only thing that you're going to see is a listing of all the matrices. So I usually put my matrix in, number 1. So, but I'll just say here, select the matrix. And then, for example, number 1, matrix A. Now, the notation for a matrix on our calculator, which is similar to our math notation, is with the square brackets around the matrix. And so the calculator, it treats differently the variable capital A if it stands by itself without those square brackets, and the capital letter A if it's inside the brackets. So you know that. 1:A. So there it is. So I'm just going to hit enter. And so the 2 numbers at the beginning are the dimensions. And so you want it to say 2 by 3. We have 2 rows and we have 3 columns. And for our convention in mathematics is to always report the number of rows first. So it's 2 by 3. To do that, you're going to hit 2, enter. I don't have to do it. And then 3, enter. So 2, enter, 3, enter. Now, if I were to say 3, enter, 4, enter, notice the size of the matrix changes. Now we have 3 rows, and then these ... over here, if you move the arrow keys, you'll see that you do in fact have 4 columns. All right, but for our example, 2, enter, 3, enter. Now let's enter these numbers in, each row at a time. So we'll type in the 2 first and hit enter, and you'll notice the cursor will move over to the right. -4 and 6. Here would be 1, -3, and 5. All right, now the matrix menu will not let you do calculations inside the menu. So what you're going to have to do is go back to your home screen. So I'm going to just put that in here. If you start typing something right now, it's going to try to put it right there in that cell location, and you don't want it to do that. So to return to home, and this is in general with this calculator, is just to hit the second key and then the mode key. Right above the mode key there is quit. And what that means is that you can quit anytime, and any screen takes you back to the home screen. So after you enter the matrix, the only other thing that you have to do then is to put the matrix in RREF form. Now on the home screen, all you want to see is RREF in a parenthesis, and then inside here you want to see the matrix where you entered in all of the elements, and I chose matrix A. And then after you see that, hit enter, and the matrix that you're after will be returned. Here's what it looks like. So again, you have to go to the matrix menu. So hit the second key and then X to the -1. Then go over to the math menu and then scroll down until you see option B, which is the RREF. Now when I hit the RREF here, notice where it puts it. It puts it back on the home screen because that's where I started. All right, now you have to enter matrix A, and there is no key on your keyboard to get those matrices, and so you have to put in second matrix again. And but this time, go to the names menu and just select option number 1. And that's matrix A. So really you just get there and you hit enter. And that's really all you need. You can close it off if you want, but then hit enter, and there's the matrix. And that's the answer matrix. And then you just kind of look down in this column and you see the XY is -1, -2. Okay, I'd like you now to try one. And I'm going to give you a big one. And you can imagine what this would be like if you tried this using some algebra. Yikes. All right, let's try number 68. So the steps would be to first create the augmented matrix. You're going to have 4 rows because you have 4 equations. Make sure that you line up in every case the x1, the x2, the x3, the x4, and then comes the vertical line, and then you're going to have that number on the right-hand side. So as you go across the first one, 1, 1, 4, 1, and then 1.3. Do the same. There is no x4 variable over here, so it's understood that it's actually 0x4. Same thing here, 0x2, because there's no x2 there. So remember to put those zeros in. They have to be a placeholder. The rest of these would look like this. All right, so what you're after here, since there are 4 variables, your solution will be like this: x1, x2, x3, x4. It's no longer an ordered pair. It's what we call an ordered quadruple, because there are 4 different components. And so your answer matrix will consist of 4 numbers, and they will all appear in that last, the far right column. Okay, so go ahead and solve it. And when you have your answer, it can look like this. Write it in the chat. It's going to be an ordered quadruple. What are the dimensions? Okay, 4. 4 by what? 4 rows? How many columns? So those top 2 numbers at the top, you got to put in 4, enter, 5, enter. It literally would take you probably 2 or 3 full sheets of paper to do the algebraic approach to this. And for the matrix approach, it treats 4 by 4 matrices in the same way that it treats 2 by 2. There's no additional degree of difficulty. All the calculations are done behind the scenes. Okay, so very good. Looks like you all have a good handle on it. Many of your problems will be like that. So this is what it looks like in the end. And another thing that you can do, and I always recommend, is that if you go back to the matrix menu and just type matrix A to your home screen and hit enter, it shows you what you typed in. So then you can check all the entries to make sure everything is correct. Because as you might suspect, if one of those numbers is wrong, then the solution will be wrong. If one of the entries is wrong. I certainly don't want to do it here, but the ultimate check, right, is you would have to put those numbers right there into each equation. So for example, x1 plus x2 plus 4x3 plus x4 equals 1.3. This first equation here, if I write it down here and then put in my values, -1.2 plus 0.6 plus 4 times 0.7 plus -0.9, does that equal 1.3? And if you evaluate everything over here, you'll see that ordered quadruple does in fact work in there. It does in fact work. And you can actually put that ordered quadruple in not just the first equation, but you can actually put it in all 4 equations, and that point will work in all 4. Works very nicely on word problems as well. The difficult part about word problems is setting them up, but after you set them up, you can then feed the matrix into the calculator and get back the answer pretty quickly. All right, Now I'm going to step back and take you through a couple of row operations. Generally, if your goal is to find the solution, then I'm not going to ask that you do row operations. But in some of our methods that you'll see later, you will be asked to do these row operations. And so just to refresh your memory, here are the legal row operations. You can swap two rows. That would be like swapping two equations. You can multiply an equation by a number. Since it's an equation, multiplying a row by a number is like multiplying an equation by a number, which means you'd be multiplying both sides by the same number, and that's a legal algebra relation operation. And the other one is to multiply multiply one row by a number and then add it to another row. And that also uses the part B, but it also, because the left and the right hand side of an equation are equal, you can add the left hand side to one part to the left hand side of another one and the right hand side to the right hand side of another one, and you have an equation that has the same solution. So, all right, so let's kind of go through a couple of these. And you have the row swap. So if here was your original matrix, here's where we ended last time. If you just swap and got the double arrow there, row 1 becomes row 2 and row 2 becomes row 1. You're going to take the second row, it becomes the first row, and the first row becomes the second row. That's a legal operation. 26. 26, it says we're going to multiply row 2 by -2, and that the row 2 gets replaced by whatever we get there. Now, since row 1 is not over here, row 1 is going to remain the same. So here's our original row 1, and because row 2 is on the right, that's the one we're changing, I'm going to leave row 2 blank for just a second. All right, so -2 times row 2 is equal to -2 times 1, -3, and 5. So here is row 2. We're going to multiply it by -2. Well, the way that we do this is we're just going to distribute that -2 throughout the entire matrix. So the new matrix becomes -2, 6, and -10. So we're going to take all of this, and this becomes the new row 2. So we take that row matrix there, and here's what the answer to 26 would be using that row operation. And maybe we'll do one other, and then I'm going to show you how you would go and do several steps to put the matrix in RREF form. So number 34 says you're going to multiply row 1 by -1/2, and then you're going to add that result to row 2, and whatever you get with that sum, that replaces row 2. So again, since row 1 is not on the right-hand side, row 1 is not going to be changed. So in your answer matrix, you can begin by writing row 1 as the original row 1. So row 1 and row 2, and we're just going to use the coefficients. So -1/2, row 1. Here's row 1, so we have to multiply each one of these numbers by -1/2. So -1/2 times -2, -4, 6 would equal, okay, so you got to bring in all your knowledge about integer arithmetic here, right? So negative times a negative is positive, and so on. So if you multiply row 1 by -1/2, this is what you get. And then row 2, all right, because we're going to add to row 2. So I'm going to bring the row 2 down. It is. And then I'm going to add those two. So if I add 1 and 1, get 2. Add 2 and -3, -1. And add -3 and 5, get 2. And then this notation over here says whatever result we get from doing these operations here, that's going to replace row 2. Now row 1 has not changed, only row 2 has. So I'm going to bring row 1 over. And then our new row 2 is this one here. And for that particular problem, that's where they want you to stop. All right, they give you a variety of ways to work with and try to understand these row operations. So now we're going to go in the reverse direction. And it's kind of just by inspection. So as you're looking at the original matrix here, and let's just take a look at number 36 here. First of all, tell me what row changed. Okay, you can hold up your fingers. Yeah, so row 2 is the same. It's row 1 that's changed. So the row operation is going to look something like this. Because row 1 changed. So the answer matrix, we're not going to change row 2 at all. Now, do you see how row 1 changed? What did they do to row 1 here to make it our new row 1 here? Okay, I see some 2's going up, and there's a times 2, a divide by 2. Yeah, so we're going from here to here. So it looks like the same operation there is the same operation here and here. And in every case, we're multiplying by 2. Now, if you look at this going backwards, then you might say, oh, you're dividing by -2, but it's really, we're going from this one to this one. So we're multiplying row 1 by 2, and that's it. And that becomes our new row 1. All right, it's not easy to figure these out, but at least you can figure out what has changed. All right, let's just take a look at maybe number 40. So which row has changed? Row 1 or row 2? Okay, good. Row 2. So in the end, row 2 is going to change, and row 1 is going to stay the same. All right, now this is tricky. We want to go from 6, -312 to 250. This one involves 2 operations. We're going to multiply one row by a number, and then we're going to add it to another row. And usually when we add to another row, it's just the row we want to change. So what would you multiply row 1 by, and then add to row 2? Anybody see it? Focus in on the last column here. And this is how you can set these up. Try a rule. How would you go, what would you need to multiply -6 by, and then add it to 12 so you get 0? Well, I saw 1, 2 there. Let's take a look. If you multiply row 1 here, oops, why was I looking at this one? Okay, sorry, I was looking at the wrong one. Here's our original. What would you need to multiply by, or -3 by, so that if you added it to the 12, you would get 0? Okay, yeah, when I point you to the right one. Yeah, 4. So if you multiply row 1 by 4, then you multiply every one of these coefficients by 4. And you would get -4, 8, and -12. If I then add that to row 2, which is still the same thing, 6, -3, and 12, and then add those two, I get 2, and 5, and 0. And that's exactly what we ended up here in this answer. So it's not so clear what row operation occurred, especially those that where you have to multiply one row by something and add it to something else. But that's what it would be. So here is the answer to number 40. And here is the answer to number 36. So what they want there is row operations. The more important skill is for you to actually be able to come up with the correct row operations so you can change numbers in the matrix on your way to putting it into reduced row echelon form. Okay, so there are, as you know, when you're solving systems of equations, there are the pathological cases, the ones that don't always work out to one solution. And so we're going to have to know when we have a system that is inconsistent, where there are no solutions. How are we going to interpret the matrix when a system is inconsistent? And then the other pathological case is the one where we have an infinite number of solutions. So how are we going to interpret a matrix if it has an infinite number of solutions? All right, that's kind of spelled out here. And this is how it would look in the 2x2 case, but we can extend that to the 3x3 case or the 4x4 case. So what you're going to notice, if you have exactly one solution, and this is our first problem, where we had 1, 0, 0, 1, 1's down the diagonal, 0's above the diagonal, 0's below the diagonal, and then we had -1, -2 here, and the answer was -1, -2. As an ordered pair. All right, here's what the matrices will look like if you have an infinitely many solutions. You're going to have the first equation, but then the second equation looks like 0x plus 0y equals 0. 0x plus 0y equals 0. Well, this means 0 equals 0. And that's an identity. That's a true equation. So if you remember when you were solving algebraic systems and you ended up where all the variables canceled and you got 0 equals 0, you would just declare infinite number of solutions. That was the same line case. Two different equations that lead to the same line. Infinite solutions. And if we rewrite this, if p is not equal to 0, if p is some other number, then this equation would be 0x, that corresponds to the last row there, the second row, 0x plus 0y equals p. Well, this is 0 equals p, and p is not a 0. So 0 equals 7, for example, is a false equation. And it's never going to be true for any value of x and y. So this is the one that if you were solving this algebraically, you would stop right here and say no solutions. And the word that we're using for no solutions is inconsistent. All right, let me just jump you up to a 3x3 and give you the same matrices if you're working with a 3x3 system. Okay, so if you have a 3x3 system of equations, the format's going to be the same. You're going to have zeros down the main diagonal. You're going to have zeros above that diagonal and zeros below the diagonal. And then your solution is going to appear over here in the right-hand column. It's going to be an ordered triple this time because there are 3 variables and 3 unknowns, 3 equations. For the infinite solutions case, you're going to have, what's key is that bottom row, because that bottom row, and I'm just putting X's here because these can really be anything in there. What's key is that in the bottom row, you have all zeros. And that's exactly what we had here in the 2x2 case, just all zeros. So look, before you write down the answer as being in the far right column, look at that last row. If that last row is all zeros, then this is 0x plus 0y plus 0z equals 0, and all of that simplifies to 0 equals 0, so you're going to have an infinite number of solutions. And the only difference over here is that That bottom row is going to be all zeros and then some number. Now, if you want MNP here, you can have that. If it looks like this, then that's 0x plus 0y plus 0z equals some non-zero number, p. And that's 0 equals p, 0 equals 7 is not true, 0 equals -3 is not true. So if p is not 0, then you're going to have no solutions in this case. So everything we did with typing the matrix in and solving the system, always look at the last row first. All right, so it's time for an example. I'm going to give you an example of a sys 3x3 system, and I want you to tell me what the answer is. So here's our example. And I'm just going to kind of make something up. Okay, solve using the matrix features of your calculator. Interpret the final, write down the final matrix, and then interpret that matrix to find out what the solutions are. So start off with the augmented matrix, enter it into your calculator, do RREF. Sometimes I prefer fractions, and so the calculator will allow you to convert these messy decimals over here to fractions just by going to the math menu here, and then converting to a fraction. If it can change those numbers to fractions, it'll do it. They're not nice, but -21/17 and -46/17. Because you have the ones down the diagonal, 1x3 is going to be this, 1x2 is going to be this, and 1x1 is going to be this. All right, you're going to be doing RREF over and over again, and you're going to type it onto your home screen. So let me show you deep recall on the calculator. If you hit second enter, here's enter. If you hit the second enter, you're going to get entry. So what this does is recall the thing that you typed in, the last entry that you typed in. Now, the last thing that I typed in was A. So when I do second enter, it gives me A. But it doesn't stop there. If you do second enter again, it'll type in that thing that you typed in 2 times before. And you can just continue to scroll back and get deep recall until you get this thing that you really want, and then you do RREF. Let's try another one, see if it works out. Here it is. 7x minus 4y plus 8z equals 11. X plus 2y minus z equals 10. 6x minus 6y plus 9z equals your favorite number. Okay, you can choose the last number that goes in. I bet you nobody selected 1 billion for their favorite number. Notice how it puts large numbers in scientific notation. 1 times 10 to the 9th. That's 1 billion. And then do the RREF and see if you come up with the same thing I come up with, although I didn't convert to fractions yet. And then what's the conclusion here? And the first thing we want to check, if you don't have ones along the diagonal, if you have a 0 in this spot, then you have to read the bottom row. The first column is the x coefficient, the second is the y, the third is the z, and then you have the right-hand side. So this bottom row, if you attach the x's with it, would be 0x plus 0y plus 0z equals 1. All of this will work out to be 0, and so you'll have 0 equals 1. And what do we conclude, or what did we include in algebra when something like that happened? Not true. 0 is not equal to 1. Never true. This is a contradiction. And in math, when you end up with a contradiction, what you do is go back and you make some statement that says, well, it doesn't have a solution. We're looking for a solution. We found a contradiction, so therefore it doesn't have a solution. All right, now for the 2 by 2 case, it looks like this, where we have 1 down the diagonal, but we don't have a 1 there. And we write 0x plus 0y equals p, 0 equals p, that's the no solutions case. If you were to have all zeros, that would be the infinite solutions case. Now the infinite solutions case is a little bit, there's a little bit more work to it. So let me give you another one and show you how you write the solution set. So here it is. So go ahead and put this into RREF. Shouldn't take you more than a minute. And then write down the solutions matrix, make a conclusion, and then I'm going to take you a little bit further to talk about what the solutions look like. Simply because of the fact that you're typing in so many numbers, it's very easy to type one in incorrectly. And so I always check the numbers. This is what I have. Can anybody confirm that? And what's the answer to this one? See, a couple of you have shared. 0x plus 0y plus 0z. Notice there are not ones down this main diagonal, so that's one of the special cases. And we have all 0. 0x plus 0y plus 0z equals 0. 0 equals 0, and so therefore we have infinite solutions. Well, gee, if there are infinite solutions, we should be able to find one. Not only that, we can find an infinite number of possible solutions. So what I'm going to do next is something that maybe you have not done in the past, but we're going to want to represent the solutions. So I'm going to write 3 equations corresponding to the 3 rows of this table. And then I'm going to show you how you write the solution ordered triple. All right, so we have the x column, the y column, the z column, and then the right-hand side. So all of the coefficients here have a variable attached to them. First row, that's 1x plus 0y minus 4/3. Sorry about working with fractions, but you're going to encounter them, equals 5/3. That would be the first equation. The second equation is 0x plus 1y minus 16/9 z equals negative 40/9. And 0x plus 0y plus 0z equals 0. So the last equation is not very interesting. It's just 0 equals 0. That tells us that we have an infinite number of solutions. The other equations are going to tell us what the nature of those equations are, or those solution is. So there's no y. So we have minus 4/3 z equals 5/3. In the second one, there's no x. And this is what the equation would look like. Using a little algebra, we're going to solve for x, add 4/3 z to both sides, and you're going to get this. A little algebra, I just added the 4/3 because it was minus here, so I added 4/3 z, but I have to add 4/3 z to both sides. And this is what it would be. And for this one, we're going to solve for y. It's nice that the calculator gives us a y coefficient of 1. Makes it much easier to solve. We're going to add 16/9 z to both sides, and the new equation will be solved for y. And here's the final answer. Now, both of our equations are solved and given expressions of z. So x equals something, y equals something, and so z is going to be called the parameter. It doesn't have a formula, But the other two coordinates, x and y, they have formulas in terms of z. So the x coordinate is 5/3 plus 4/3 z. And the y coordinate, oops, it's down here, is 16/9 z minus 40/9. Now you might not realize it, and that might look complicated, but there's your infinite number of solutions. All you have to do is to choose a value of z and plug it in there, and you will get a solution to the system. There are an infinite number of solutions. So if you choose z to be any one of an infinite number of possible values, you will get a solution to this system of equations. By that, I mean this. The easiest number to put in for a variable is z, or is 0. If z is equal to 0, then the ordered pair becomes we're just going to replace all the z's with 0 and leave everything else alone. Well, if z is 0, then I just put 0 in the third coordinate spot. And this one simplifies because 0 just makes the whole term go away. 5/3, -40/9, and 0. That there is one solution among an infinite number. If you put those three coordinates into our three equations, it will satisfy all three equations. If you want another solution, choose a different z value. If z is equal to 1. And because you can choose z to be an infinite number of possible values, you're going to be able to identify all of the solutions that work. Here we put z as 1, so the last coordinate is 1. And you have to simplify. 5/3 and 4/3 is 9/3. And 9/3 simplifies to 3. 16/9 minus 40/9, what's that, 24? -24/9. And then the z coordinate is 1. If you want another solution, choose z to be 3, z to be 9, z to be 100. Any number you choose will give you a solution, and these solutions will work. They're an infinite number. We should be able to find one. And here's how you do it. Okay, I'm going to show you Gauss-Jordan and with the row operations, and we'll start off with just a small one in the time we have left. I don't know for, let's take, let's say, well, let me write the system first. It's going to be a small one because these calculations are fairly tedious. So 3y equals, and let's do 2x minus 3y equals, and let's say that the solution is, again, just making up a problem here. How about we want the solution to be 2, 5? Nice round number. So 2 and 15 is 17, and 4 minus 15 is -11. Okay, so for that system, the 0.25 is a solution. I don't think it has an infinite number of solutions, so let me show you Gauss-Jordan using row operations. Generally in problems on exams, I give you a row operation and I just say carry it out. So we start off with the first row, the augmented matrix, the second row of the augmented matrix, and it looks like this. We want 0 there, so the first number we're going to try to get rid of is that 2. Ultimately, we want our final matrix to look like this, where your solution is over here, 2, 5. We want it to look like this. So we want a 1 in this spot, and we want a 0 in this spot. We've already got the 1 in this spot, so we need to put a 0 in this spot. So I'm going to use these two coefficients. I'm going to multiply row 1 by -2, because if I do that, I will have a -2 there. And then if I add it to row 2 and make that the new row 2, then a 0 will end up right there. All right, so -2 row 1 is -2, -6, -34, and row 2 is 2, -3, -11. So if I add -2 row 1 plus row 2, that is, add these two row matrices here, you're going to see the 2 and the -2 add up to 0, and that's what's going to give me a 0 in that spot right there. These numbers add up to -9, these add up to -45. And then it says that becomes our new row 2. So since we're only changing row 2, row 1 remains the same. Row 2, however, is our new row 2. So the order we want to put these numbers in, we want to put a 1 here first, and then we want to put a 2 here next, then we want to put a 1 here, and then we want to put a 0 there. Those 4, so you're going to have 4 different row operations. All right, so for the next one, we're going to we want to put a 1 right here. So we're going to take row 2 and divide it by -9, because 9 divided by -9 is 1. And what we get will become our new row 2. So row 2 divided by -9, I take 0 divided by something, it's going to remain 0. If I take -9 and divide by 9, that's going to be 1, and that's what I wanted. I wanted a 1 in that spot. And then if I take a -45 and divide by -9, I get 5. And we are changing row 2 here. So our row 2 becomes then 5. One last one. We're going to take row 2 and multiply it by -3, because if I multiply that by -3 and then add it to row 1, and then let that become the new row 1, then I will have a 1 in that spot, and I will preserve the 1, 1, 0 here. So if we take -3 row 2, multiply row 2 by -3, 0 times -3, 1 times -3, and 5 times -3, we're going to get those numbers. All right, so it takes care of this one. And then we're going to take row 1, which is our current row 1, and then we're going to add them together. So when you add them together, add component-wise, and you get this. And that becomes the new row 1. So in the end, the new row 1 is 1, 0, 2, and we didn't change row 2 in that last one, so it's 0, 1, 5. And we've got it in the format we want it, the reduced row echelon form. And so you can see that the answer is 2, 5. And so we converted the original one to the answer matrix, and now we know the answer is 2, 5.